folks, so this first one is a linear function because there's no square root symbol, there's no power, there's no absolute value symbol, there's nothing interesting going on with it. It's just y equals mx plus b. So for the parent function, you can say linear. And let's go ahead and state what our basic table for that parent function is. What three values do we use for x? Negative 1, 0, and 1. And what we're going to find is that we can use those same three values pretty much with every function except which one? What function can we not use those three values with? The square root one, because you can't take the square root of a negative. So my parent equation looks like y equals x, and if I plug in those values, negative 1, and 0, and 1. Very, very good. Now, transformation-wise, when we go to describe these, we've got a negative 1 on the outside. Now, we consider this one on the outside because it's not inside parentheses or some sort of function symbol like we have on some of these other ones. So this is outside, so we think of our arm going down. So the inside ones, we cross our eyes and it goes in the opposite direction of what we would expect. Those outside ones are consistent. There we go. So what about that negative being multiplied out in front? You could put a little implied coefficient of 1 there, but if it's negative 1 times x, anytime we have a multiplier in front, that is going to be indicative of either a vertical reflection or a vertical stretch or shrink. What does the negative automatically do? Vertical reflection. So the negative being multiplied out in front is what swivels it across that x-axis. So vertical reflection for that one. And you can either say vertical reflection or over the x-axis. Now looking at this one, we've got f of x equals 1/2 times x minus 1 cubed. What type of function is this if it's cubed? A cubic function. So y equals x cubed. Now, for our parent table, what three inputs can we use? Same as the linear one, negative 1, 0, and 1. And when we plug those in, negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. And remember, folks, we have to be able to write all of those parent tables because that is what we use to transform our equations in order to graph. So transformation-wise on these ones, that minus 1 is on the inside of the function. It's inside our parentheses. It's inside the cubic function. So this is when we cross our eyes because it does the opposite of what we would expect for that sign. So does it move left or right? It moves to the right. So this is right 1. So the outside transformations do what you would expect with the sign, so negatives move us down, but those numbers on the inside do the opposite of what you would expect with the sign. So then what about that 1/2 being multiplied out in front? Vertical shrink, very good. So anytime it's a number being multiplied that's between 0 and 1, that is going to vertically shrink your function. What about this minus 3 on the outside, on the next one? Down 3. And that minus 2 on the inside, cross your eyes, opposite of what you would think. Right 2. And then what about that negative getting multiplied out in front of that function? Vertical reflection. And what do we call this parent function? Absolute value, or if you're lazy, abs-val. There is what the parent equation looks like, just y equals the absolute value of x. And I can use those same three inputs, negative 1, 0, and 1, and I can take the absolute value of them, take the absolute value of negative 1, or what happens when we put that in the washing machine, we get a positive 1. Absolute value of 0 is 0, and absolute value of 1 is 1. All right, folks, tell me what the next function is. Quadratic. That little power of 2 is our indicator for a quadratic function, so quadratic. Now, this one is a little bit tougher. I would actually put a star by number 4. We've got a +1 on the outside. Those outside transformations consistent with the sign. That's going to move us up 1. The inside transformation is going to move us left 1. Now, the reason we have starred this problem is because of this -3. Sometimes students look at that and they go, well, it's negative, so like, is that a small number? Is it a shrink number? What's tricky about this one is that one number, -3, is 2 different transformations. The negative is a vertical reflection. Anytime we have a negative getting multiplied out in front, it is a vertical reflection. But then I consider the 3 itself separately. Is that 3 a stretch or a shrink number? That is stretch, so vertical stretch by 3. And folks, actually on this one, when I said vertical shrink, I should include the by 1/2. Including the by 1/2 or the by 3 is important because that tells you how you are going to start manipulating your parent table. So then x, -1, 0, and 1. 1 squared in the parent function. Sorry, -1 squared in the parent function is 1. 0 squared is 0. 1 squared is 1. Now, what we need to be careful about with quadratics is that their parent table is exactly the same as an absolute value function table. So these two tables are exactly the same. So how do we tell them apart? We should know that this graph looks like a V. And what does a quadratic look like? A U. So just make sure when you are connecting those points or when you start to go outward from these 3 central points that you curve for the quadratic but make a straight V on both sides for the absolute value. So let's go ahead and take a look at our next one. We see a square root. So this is a square root function. And the square root functions have their own unique parent table. We can't start with -1 because that is not possible on our calculator. So what is the first input that we can plug in? 0. 0 is our first thing that we can take the square root of. So for my parent equation, y equals the square root of x, the square root of 0 is 0. And if you aren't sure, you can try it on your calculator. The square root of 1 is 1. Am I going to plug in 2 or 3? No. Next thing I'm going to plug in is a 4. So these values are different, and what I want you to notice about these values is that they are all perfect squares. And the square root of 4 is 2. All right, folks, so on your own, I want you to list out the transformations for this one and try the next problem. All right, folks, go ahead and check yourself. So for the square root one, we've got a 3 getting multiplied, vertical stretch by 3, plus 4 on the inside. We cross our eyes, and that positive 4 moves us left 4. Minus 2 on the outside is going to move us down 2. Next one is a cubic. Now, how do we know that that plus 5 is on the outside? Not in parentheses. It's not inside getting cubed with x, so that is on the outside. So up 5, and then the 4 is being multiplied by x cubed, so that's going to be a vertical stretch by 4. So folks, what questions do we have about the transformation rules or those parent tables? The next thing that I would like to do with these transformations then, before we talk about the graphing together, is I want to talk about how we turn these transformation descriptions into actual things we're going to be doing with the table. So when you turn these into actual transformations that occur for the table, you need to consider if they affect X or Y. What transformations affect X? Moving left or moving right? What transformations affect Y? Moving up or down? What other transformations are affected? Vertical stretch and shrink.
Nyla Sandoval, please come to the attendance office.
And vertical reflection. This is very, 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 very important. These two things affect X, and all four of those things affect Y. The other thing that's tricky about the X part is it switches signs from the equation. And that can get pretty confusing because it's like we're crossing our eyes and it does the opposite of what we would expect for the sign. But then when we actually use that to transform our parent table, we use the opposite sign. So folks, we are just going to show what we would do to each of these parent tables using those transformations. So folks, starting with number 1, do I have anything that's affecting X? Nope. So vertical reflection and down 1 are both affecting Y. So my X values are going to stay the same. So these parent table values will remain the same. And what shall I do with these Y values? We are going to take the opposite of them. So negative of each of those Y values. That's how we vertically reflect them. And then we are going to subtract 1. So it's like we're kind of doing the same thing that it's doing in the equation. I'm multiplying by -1 to each of my Y values, and I'm moving them down 1. So folks, what we now do is plug in our Y values into this kind of transformation expression. So -1 is a +1, and 1 minus 1 is 0. New Y value. -0 is 0, -1 is -1, and then -1 minus 1 is -2. You can use your calculator for that to check your integer rules, and then our X values stay the same. So folks, on that homework, when I say show your table work, you're looking for, and this transformation stuff is going to come back to haunt us in the next part of this chapter as we start looking at inverse functions and how to graph them. So I want to make sure we're solid on this before we move into the next section. So let's go ahead and take a look at our next table, and we won't write the transform. Are we pretty good with making the transform table with that part of it? Okay, it's this part that I want to make sure we're good on. So can we decide what we're actually going to do with those values? So let's take a look at the next one. Do I have anything affecting X here? Yep, moving right 1. Now, for your X ones, those left rights, the sign switches from the equation. So we are going to apply X plus 1 to our table. What are we going to have for our Y transformation? How do we shrink them by a half? 1/2 Y. We multiply each Y value by a half. Folks, I'm going to turn you loose on the next one. See if you can decide on this part, how you're going to transform X and Y. You've got one transformation affecting x and two transformations affecting y. For your x values, you're going to have x plus 2 to move those right 2. And then to vertically reflect and move down 3, you'll take the opposite of the y values. That's how we vertically reflect. And then you'll subtract 3. Questions? And then what you would do is you would apply this to each of those x values, apply this to each of those y values, and that's how you get that new transformed table. So folks, I want you to try, actually we'll go through number 4 together since this one's kind of tricky, and then I'll turn you loose on the next two. So here, we've got left 1. That's the only thing that's going to affect x. So what are we going to do to move my x values left 1? X minus 1 or plus 1? Minus 1, opposite of the sign that you have in the equation. Now for the y's, we have 3 different things that are happening. Vertical reflection, vertical stretch by 3, and up 1. It kind of mimics exactly what's in the equation. I've got negative 3 being multiplied, so negative 3 times all the y values. Then what shall I do to move them up 1? Plus 1. Now, folks, I did say that you could break this down into 2 steps if you wanted to triple by negative 3 and then add 1. Just make sure you are doing the multiplication first. So if you break it up into 2 steps, you do have to follow PEMDAS, and you would want to handle the multiplication by negative 3 before you add 1 to it. So, folks, with that in mind, I want you to go ahead and try the next 2 problems. Compare your answers with someone sitting close by to you. You just hold up your paper and say, look. So x minus 4, 3y minus 2, same, nothing happening to our x values there, and 4y plus 5. Raise your hand if you got those both right. Okay, good. Hopefully we're starting to feel a little bit better about those. So now, folks, we are going to take one of these graphing problems in exactly the same way that we did those top ones. Our final step will just be creating the table, applying those transformations, and then graphing those points. So the first thing we want to do with this problem is identify the type of function it is. What is it? Square root. And the square root equation looks like y equals square root of x. Without looking above, can you generate that parent table? 0, 1, 4. All those perfect squares. And if you go, oh no, what if I forget? Your calculator's going to tell you, hey, you know what? You can't actually take the square root of negative 1. And if you try to take the square root of 2 or 3, you end up with one of those nasty decimals. You can work with those, but it's a lot easier to graph if you stick with the perfect squares. So then 0, 1, 2. So folks, let's go ahead and graph our parent function. 0, 0, 1, 1, 4, 2. And remember, your square root function looks like half of a sideways parabola. So it's got some curve to it, and it starts from the vertex and goes out into the right. So 0, 0 is always our vertex point or central point for all of these parent functions. So now, here's what I would like you to do. Describe the transformations in words, and then decide on what you are going to do to the X column and Y column of the table. Transformation descriptions, vertical reflection, right 2 and up 3. So what's affecting X is the right 2. So to move our X values right 2, we use X plus 2. Opposite sign than what's in the equation. Now for our Y values, we're going to vertically reflect them by taking the opposite of the Y values and then sliding up 3. And again, folks, it's pretty similar to what we have in the equation. It's a -1 times the radical. It's a -1 times our Y values. And then we add 3, and then we add 3. So then our transform table is going to look like this. I'm going to add 2 to all my X values. So 2, 3, and 6. And now I'm going to take the opposite of my Y values and add 3. Opposite of 0 is 0, plus 3 is 3. Opposite of 1 is -1, plus 3 is 2. Opposite of 2 is -2, plus 3 is 1. And now we are going to plot these transform points. Keeping in mind that this first point is the transformed version of the vertex. So if 0, 0 was the vertex here, here's my new vertex at 2, 3. And that's important for helping you draw the direction of the swoosh. So then 3, 2, and 6, 1. So this top point is the vertex. So then I'm going to curve down through those points. Does that look consistent with what we described? Does it look like our vertex moved right 2 and up 3? Yep. Does it look like it has been vertically reflected top over bottom so that instead of swooshing up, it is swooshing down? Yes. So that ensures that our graph matches what we stated for our transformations. Folks, the last thing that we're going to be doing with this is get a little bit more practice with domain and range. So folks, domain values are X values getting covered by my graph. We're going to ignore the parent function and we're just going to do it for the pink line. So if I am looking at my X values and instead of doing lines with my marker, I'm just going to color in this whole area. What X values are getting covered by that pink line? Where do those covered X values start? At 2. So they start at 2, and then they go infinitely to the right. Using inequality notation, you would say X is greater than or equal to 2. Using interval notation, you would say bracket 2 to infinity. Making sure you use a parenthesis on the infinity sign and a bracket around the 2. Now, the range is the Y values. I start at a Y value of the vertex, and then I'm covered going down, and this arrow is going to keep curving downward. So where do my Y values start? At 3, and are we covered going up from 3 or down from 3? Down. So Y is less than or equal to 3, or in interval notation, this is the tricky one. If you've been making friends with interval notation, beware of when it's less than or equal to. We start from the bottom at -infinity, and we end at 3. So interval notation is always negative to positive in the y direction, negative to positive in the x direction. So that would be our domain and range for that one. What questions do we have? I want you to try number 8 completely on your own. Make the parent table, make the transform table, state the transformations, and then state the domain and range.